Alright, hello everyone, what's up? Welcome to this live session at Catalysis by Vedantu. My name is Pahul and I'm an alumnus of IIT Bombay. If I'm audible and visible, please write you in the chat box, you know the drill. And in the previous video that I took for the revision of chemical bonding that was live, I got this feedback that sir, please take live videos for revision because somehow it's a little more fun. So, taking in your request, today we are going to try and revise GOC as fast as possible. You know how these videos work, yes? So the thing about GOC is that the revision of GOC is incomplete without solving questions, and hence today's session as well as tomorrow's session at 8 p.m. of solving GOC is very important. Still, let's try to brush up all the concepts that were there in GOC, and tomorrow while solving questions we'll do a lot of advanced level examples as well. Alright, so if you are ready in 3, 2 and 1. Okay people, so what we have over here is the first concept of general organic chemistry, that is the bond fission. Bond fission implies breaking of a bond. You have two types of bond fission. First is heterolytic and the second is homolytic. Sometimes bond fission is also known as bond cleavage. In terms of heterolytic fission, what happens is the bond between two atoms is broken heterolytically, which implies that the two electrons that are there in this bonded pair of that is a bond, will shift towards one particular side that is represented by this full arrow. So if it is broken in this particular manner, the right hand side carbon will get a negative charge because now it has one extra electron. Why one extra electron? Because this was one of its own electrons, yeah, and the other electron which we've drawn in green color over here belonged to the other carbon, but now it's taken both. So there is one extra electron on this particular carbon. And let me keep the color scheme consistent. This is the red one and this is the green one. So because of this extra green electron, you are getting a negative charge. Fine. The other carbon will become a carbocation. It is deficit in electrons. It has an extra proton now, obviously. So we'll call it a carbocation. Cation and anion, everyone knows that. And then a fancier way of breaking a bond is when you have homolytic cleavage or homolysis. This happens in cases where the electronegativities of both sides are very similar to each other. Yeah. So in this case, as you know, there are two electrons in this bond. Each of these electrons will be given to these atoms. Okay. So one of them goes to the right hand side, one of them goes to the left hand side, and what you get out of this are two carbon-free radicals. These carbon-free radicals are very similar to neutral carbon atoms because they are neutral. Always remember that carbon-free radicals are neutral species. They do not have any charge, but their octet is incomplete. Yes, their octet is incomplete, and experimentally we found out that carbon-free radicals are very reactive. Their reactions are very random, very violent, and sometimes they end up exploding in the laboratory as well. Okay? So you get carbocation, carbon and carbon-free radical. Carbocation and carbon-free radical are electron deficit in nature. Carbanion is electron rich in nature. Fine, we understand this idea. Then, my dear friends, we'll come back to the stabilities of these intermediates that we've drawn. Okay, so carbocation, carbanion and carbon-free radicals, these are known as reactive intermediates. Everyone knows that. Why intermediates? Because these are formed in the middle of a reaction. So they are like the beach ka bandar of a reaction, the middleman. Fine, so we'll come back to the stability of these reactive intermediates, but we need to think about the electronic effects. Now, what are the electronic effects that we need to think about? We have the very famous inductive effect. Yes. What's happening with inductive effect? Inductive effect is a permanent effect. It propagates via sigma bonds and it happens because of electronegativity difference. Yes, so if I have a carbon bonded with a fluorine, the fluorine will get a partial negative character, carbon will get a partial positive character. We've understood this in dipole moment in chemical bonding, and this effect will carry through the entire carbon chain. So there could be certain elements, there could be certain atoms that try to take electrons from the entire ring. There could be certain elements that try to give electrons into the ring. Yes, so those two cases could be written as the first case where there is electron withdrawal. As you can see, this positive character, this partial positive character will propagate through the ring, propagate through the chain. Yes, and with every carbon atom it keeps on diminishing. This effect is almost negligible after the third carbon atom. From the fourth carbon atom, this effect is almost negligible and happens via sigma bonds. It's a weak effect. So this one over here, where you have an electron withdrawing group, this effect is known as the minus I or negative inductive effect. Similarly, if you have an electron donating group, you will have partial negatives propagating through the carbon system, and that is known as the plus I effect. Now let us talk about the order of plus I and minus I groups. Minus I groups mein, this is the order. You can pause the video right now and take a screenshot and look at these. Very obvious. Nitrogen with a positive character and a lot of electron withdrawing groups on it. This wants to pull electrons as much as it can. Yes. Similarly, if you notice, all of these groups that we've drawn over here have certain electronegative atoms in them. Yes, nitrogen and 2 oxygens, of course electronegative, wants to pull electrons towards itself. Carbon with 3 oxygens, of course electronegative, wants to pull electrons towards itself. All the halogens, very nice. Fine. And then at the end you have the hydrogen atom, which is the standard for us. Okay, hydrogen is the middle point between minus I and plus I. That is why it is kept at the end of this table. So in case you want to take a screenshot of this table, 5, 4, 3, 2 and 1, you can pause the video over here as well. Then going to the plus I groups, these are the ones that will give electrons into the system. Notice all of these systems that we have over here have some or the other problem with having electrons on their own. Negatively charged carbon doesn't want that carbon. It will try to push the electrons into the ring as much as possible via the sigma bonded chain plus I effect. Nitrogen with a negative charge, oxygen with a negative charge, yeah, all of these will try to donate electrons into the system via inductive effect. Inductive effect happens via sigma bonds. Similarly, CH3 groups, why are these electron donating in nature? Because carbon versus hydrogen, hydrogen's electronegativity is 2.1, carbon's electronegativity is 2.5 on the Pauling scale. So over here there is a tiny dipole moment in the carbon's direction. Yes. Now when you combine all of these dipoles, it ends up pushing electrons inside the chain. Okay. So this is the order. Once again you can look at it. 5, 4, 3, 2 and 1. In case you want to take a screenshot, please do so and pause the video in case you want that. Cool. Now, आगे बढ़ते हैं. What is this that we are talking about? This, my dear friends, is resonance, isn't it? Something was expected, but the reality was entirely different. Expectation was that ozone looks like this. What is this bond? This is a coordinate bond. Yes. Benzene had this kind of a structure earlier, the Kekulé structure. Yes. But in reality, what happened was, ozone has all the bonds symmetrical. Yeah, its length is given, the angle between these oxygens is given. So the reality is a little different than the expectation. The electrons are very beautifully shared amongst all of the atoms. Similarly for benzene, I'm pretty sure you draw this structure all the time for benzene. All of the bond lengths over here were 1.4 angstroms approximately. Over here it was expected that this bond would be shorter, this would be longer, this would be shorter, this would be longer. That's not the case. So when we went from the expectation to the reality, we gave the idea of resonance. What is resonance? Resonance is nothing but the imaginary idea of delocalization. Okay, delocalization of electrons. As we see over here in the first picture, we've localized these 2 electrons between just 2 oxygens. When we divide these electrons with the other oxygen as well, we call it delocalization. Okay, so resonance is essentially just delocalization of electrons, and we understood eventually that it gives more symmetry to the molecule, it gives more stability to the molecule, and we've discussed the idea of resonance energy in thermodynamics as well. Where can resonance occur? What do we need? We need parallel orbitals. What kind of parallel orbitals? We could have pi bond orbitals parallel to each other. We could have non-bonding electron orbitals parallel to each other. For example, those lone pairs. We could have vacant orbitals. And the examples of all of these cases are given towards the right hand side on this particular page. Yeah, the first structure is of a diene. If we notice on each of these carbons, there is a p orbital, and all of these p orbitals are parallel to each other and they can show resonance. Similarly over here, there are 3 orbitals that are parallel to each other. These 2 are p orbitals that have these 2 electrons, and then you have a vacant p orbital. Do you realize? I'll write over here, vacant. Why is it vacant? Because it has a positive charge. Fine. Then you have p orbitals, and then you have this nitrogen's orbital in which there is this lone pair, parallel resonance. Okay, this one as well. You have this orbital parallel to the p orbitals, which has the negative charge, resonance. You have a free radical case as well. Yes, this free radical orbital is parallel to the orbitals that exist on these carbons. ठीक है जी? Fine. So my dear friends, in all of these cases, resonance can occur. Delocalization of electrons is what it is. And after we understood delocalization of electrons, after we understood what are the cases of resonance, we came into the idea of resonating structures. Yes? Resonating structures. Okay, this is a very interesting idea. My dear friends, always remember that resonating structures are 100% imaginary. Yes, resonating structures are 100% imaginary. Resonating structures do not exist in nature. What exists in reality is the resonance hybrid or resonating hybrid. Yes? Do you remember what is the resonating hybrid? Let's just try to draw it for the structure on the screen. This structure is known as aniline, I'm pretty sure you know. Let's just try to draw one resonating structure of this and quickly jump to the resonating hybrid. So what will happen? This nitrogen will try to push electrons into the system. This will go towards this side, and what you get after this, you separate these two resonating structures with these double-sided arrows. You make a hexagon. Of course, now nitrogen over here has a double bond, NH2. Nitrogen will capture a positive charge now because it has given one lone pair away. Nitrogen having 4 bonds implies it has a positive character. The negative charge has moved over here, and this is what it looks like. Eventually, when you keep drawing these resonating structures, you will end up with a resonating hybrid that is sort of the average of all of these resonating structures. Yes, and what will that look like? Let's try to draw the resonating hybrid. First of all, a hexagon, then on top of it there is a nitrogen with H2, and the hybrid looks something like this. Partial bond from this nitrogen to this carbon, and then partial bonds all over this aromatic cycle. Yes, we generally just draw it like a circle, but I'm making a little more elaborate diagram over here. Yes, and this nitrogen will capture a partial positive character as we have understood over here. The carbons at the ortho positions and the para position, yes, will capture partial negative characters. At meta, the effect of the resonating group will not be found. And with that, I remind you a trick of mine where I always say meta no meso. We'll discuss that idea in questions in tomorrow's class as well. So this makes us understand that resonance can happen in two ways. You can have groups that donate electrons into the system via these parallel orbitals, via these pi orbitals, or you can have groups that withdraw electrons from these structures. These groups that I've shown you over here are the plus M groups. Plus M bole to, these will donate electrons into the system. So for example, you have CH2 with a negative charge. This negative charge will be pushed into the resonating system. Similarly, you have NHR, nitrogen has a lone pair. This lone pair will be pushed into the system like it was pushed over here. Fine. Similarly, OR pushed into the system, lone pair, very nice, pushed into the system, so on and so forth. So this is the order. It continues like this. Okay, this is how the order continues. This is the direction of the order. I'll give you 5 seconds to take a screenshot. Otherwise, you can pause the video as well. 5, 4, 3, 2, and 1. So in all of these cases, you will realize there is either a negative charge or a certain lone pair that is present on these particular systems that can be donated into the rest of the carbon chain or the ring. Moving on to minus M. Minus M, of course, will be places where there is a deficiency of electrons. Fine. So positive charge carbon. So it will want to pull electrons from the resonating system. It will want to pull pi electrons towards itself. Similarly, NO2, it's a very good electron withdrawing group according to resonance. Yeah, this is what the structure can be drawn as. And double bond O always wants to pull electrons towards itself. Always remember, double bonded electronegative atoms like double bond O, triple bond nitrogen, this sulfur with double bond O, these want to pull electrons towards themselves. Okay, pulling electrons, so on and so forth. So this is the order of minus M groups. It is very logical once you go through it, and I'm pretty sure since this is a revision session, you already know what these are. Fine. So take a screenshot of this. 5, 4, 3, 2, and 1. And you can pause the video as well. Then came the idea of the stability of resonating structures. Yes, talking about the stability of resonating structures, there are just 4 things that you need to remember. These are written at the bottom of this page. First of all, the structure with most number of bonds will be the most stable. Most number of bonds will automatically imply most number of octets. You don't need to consider those 2 rules as different. Okay, most bonds is most stable. Then lesser number of charges are more stable. Less charge separation is more stable. Then if unlike charges are close and like charges are far, and then if you have negative charge on the electronegative atom, carbon, or I'll just write atom over here, then the resonating structure is more stable. So this is the order of priority of these. Okay? My dear friends, do me a favor and please, for tomorrow's class, remember this order. Okay, remember this order of priority. First priority goes to most number of bonds, second priority goes to less number of charge separation, third priority goes to charges being closer if they are opposite to each other, charges being far if they are like charges. Positive and positive should be away from each other, obviously. And then if every one of the first 3 statements is true for all the resonating structures, then you resort to the last statement that negative charge should be on the more electronegative atom. Okay, so just to give you a quick example, okay, if you have a particular structure like this, I can make its resonating structure by pushing the electrons in, and the resonating structure will look something like this. Can you tell me which one of these is the most stable? If you simply look at point number 4, you will get an incorrect answer. The correct answer is that the second structure is more stable. Why? Because in the second structure, you have more bonds than the first structure. In the second structure, all the octets are complete. In the first structure, this carbon has an incomplete octet. Fine, great. Remember this order for tomorrow's question solving class because we will use this extensively. Awesome. Now moving on to the next idea of general organic chemistry, and that is hyperconjugation. Yeah, why do we call it hyperconjugation? Well, because this is like conjugation. Conjugation is just a fancier word for resonance, but hyperconjugation is something that's a little more tricky, but still is a very good theory to explain whatever we have found in chemistry. So over here, let's say there is a carbon, and the carbon next to it, okay, carbocation, the carbon next to it is just a simple sp3 carbon. It cannot provide its stability via resonance. So what is theorized is that this hydrogen, for a temporary, tiny, little, indistinguishable, small span of time, can break its bond and give you something that looks like this. Okay? Do you realize what has happened? You have essentially broken a sigma bond. So this hyperconjugation is also known as sigma bond resonance. It is also known as no bond resonance. Just fancy words for hyperconjugation, okay? So no need to worry about the nomenclature over here. Fine. So over here, do you realize that negative and positive close together, I can essentially form a double bond out of this. And obviously, these 2 structures that I've drawn are imaginary, so we will put them in the square brackets. Whenever you are making resonating structures or hyperconjugating structures, you have to put them in square brackets. Alright, now my dear friends, if I have to make the hyperconjugating hybrid, what exists in reality, the hyperconjugating hybrid, it will look something like this. Okay, this bond is a little less than a single bond. Okay? This bond with hydrogen is not exactly a single bond, its bond order is slightly less than 1, very slightly less than 1. And over here, there will be the presence of this partial bond as well. Very slightly more than 1 bond order will be there for this bond. Okay, and the carbon over here, which is involving in the breaking of the hydrogen atom, this will carry a negative character. This will carry a positive character, and this will also carry a positive character. This is the final hybrid that exists. Also remember that hyperconjugation can give stability to double bonds, positive charges, and carbon-free radicals. More alpha hydrogens, I'll write over here, more alpha hydrogens implies more stability. Once again, reminding all of you guys that this is a revision class. If you do not know what alpha hydrogens are, if you do not know what double bonds are, then please go back and do your entire 11th class once again and 12th. Okay, so this is just a revision class. We are brushing through the concepts quickly. Applying the ideas of inductive effect, resonance and hyperconjugation onto this. This is the general order of stability of carbocations. Everyone should remember that tertiary carbocations are most stable, then secondary, then primary, then methyl. The same order is applicable for carbon-free radicals as well. Do you remember? The same order is applicable for carbon-free radicals. So, always remember, always remember that tertiary carbocations, carbon-free radicals are more stable than secondary, then primary, than methyl. And hyperconjugation is at play over here because if we look at the tertiary case, there are the most number of alpha hydrogens. Alpha hydrogens are the lines that I've just drawn in the green color. Okay, as simple as that. Then going to methyl. Now going to methyl carbocations, primary carbon ions. Sorry, yeah. If we talk about carbon ions, in carbon ions, do you realize that hyperconjugation cannot give them stability? Because in hyperconjugation, the hydrogen bond breaks and gives the carbon atom the electron. यहाँ पे जो अपन ने bond तोड़ा है, I accidentally made the opposite arrow over here. This arrow is towards the carbon. Let me make that correction quickly. So you realize that this bond breaks towards carbon because carbon has more electronegativity. Yes, fine. So we understand that if this hydrogen's bond breaks and gives this carbon a negative charge, negative and negative right next to each other will not give any stability. So hyperconjugation does not play any role in the stability of carbon ions. Fine. That is why in carbon ions the order is opposite. Carbon ions want to be the least bothered. Okay, carbon ions want to be the least hindered. More hindrance implies more inductive effect. You don't want that. Fine, you don't want to give more electrons into the carbon ion. So methyl is the most stable, then the primary, then the secondary, and then the tertiary carbon ion. This completes the basics of the electronic effects in carbon and its chemistry. ठीक है, फाइन. सो ऑर्गेनिक केमिस्ट्री का जो सबसे बेसिक पार्ट है वो तो अभी अपन ने कवर कर लिया इन द फर्स्ट 20 minutes. Now moving on to aromaticity. Do you remember what aromaticity is? Aromaticity is just those specific cyclic cases where you have more stability than what you expected. It is a very fancy form of resonance, if you may. So aromaticity, the recognizing criteria was given by Huckel as Huckel's rules. And in essence, Huckel's rules especially says that you need to have a cyclic planar conjugated system. Yes, and the number of electrons in conjugation should be equal to 4n plus 2. Remember 4n plus 2 rule? 4n plus 2 electrons, essentially it implies that you need to have odd number of electron pairs. As simple as that. No need to do 4n plus 2 all the time, just count the number of electron pairs. So for example, in the first case, cyclic structure, planar structure, conjugation exists. How many electron pairs in resonance? 1, 2 and 3. 3 is an odd number, so this is aromatic. So the first structure is aromatic. Yeah. The second structure, 1 electron pair, 2 electron pairs. 2 is an even number. This makes the structure anti-aromatic. Anti-aromatic structures are unstable. They are more unstable than expected, and they are very hard to form in the laboratories, and they are not found in nature either. Fine. The next structure, if you would count these number of electrons, 1, 2, 3, 4, you would say, okay, this is an even number, it has to be anti-aromatic, but it is a huge structure, it is smart enough on its own, and this is one of the first exceptions of general organic chemistry. The shape of this particular molecule looks like this. Okay, it is a boat-shaped molecule. If you would remember, this is known as cyclooctatetraene, also known as COT. And it exists in a boat-like fashion. It does not exist in a planar way. It exists in a boat-like fashion. Because of this boat-like fashion, there cannot be conjugation because it is not planar, and it avoids being anti-aromatic. So this structure of cyclooctatetraene is in fact non-aromatic. Okay, very beautiful exception. Everyone remembers that, I'm pretty sure. Then let's come to more annulenes. Everyone knows benzene is aromatic, so we're not talking about benzene. Then let's come to further annulenes. What is this? This is 10-annuline. My dear friends, over here what happens is you have these two hydrogens. There is repulsion between these two hydrogens. This dihedral interaction exists between these two hydrogens. Because of these two hydrogens, this ring cannot be planar. Okay, no planarity because repulsion. If it was planar, it would have been aromatic, but there is no planarity because of this repulsion. And my dear friends, 10-annuline is non-aromatic. Okay, then you have 12-annuline. Count the number of electrons: 1, 2, 3, 4, 5, 6. 6 electron pairs. You would be like, this has to be anti-aromatic. It looks very planar. But once again, this structure is so huge, it knows that if it was planar, it will become anti-aromatic. It doesn't do that. This is a non-planar structure once again. And this, yet again, is non-aromatic. Okay. 14-annuline. Then let's come to, what is this guy? Sorry, this is 12-annuline. Okay. 12 carbons, 12-annuline. Then let's come to 14-annuline. 14-annuline is very beautifully aromatic to look at. But my dear friends, it in science is known as mildly aromatic. Okay, why is this so? Because when we do experiments on this 14-annuline, we realize that even though it is aromatic, it is planar, it does not have an exceptional stability like benzene. It does not have that exceptional stability that's there for aromatic structures. So this is, technically speaking, it is mildly aromatic. It does not show the characteristics of a typical aromatic structure. And then you have the 18-annuline. 16 is obviously non-aromatic. You can count that if you want to. Then 18-annuline, this is very beautifully aromatic once again. So I'm pretty sure you realize that in chemistry, a lot of things depend on experimental evidence. This is what we have. Annulines also revised. Fine. After aromaticity was done, then came isomerism. And isomerism is one of the most interesting topics that you could ever have in general organic chemistry, in chemistry in general. Okay. So structural isomerism has 3 categories: chain, position and function. Isomerism is when you have the same overall formula for 2 different structures, but when you look at them deeply, you realize that they are different from each other. So you have structural isomerism and stereoisomerism. Structural has 3 forms: chain, position and function. In the first case, you realize that both of their chemical formulas are the same. Both of them are alkanes. The first one has 5 carbon chain. The second one has a 4 carbon chain principle with 1 substituent, although both of them have the same overall condensed formula. Yes, so the longest chain is different. I hope you remember nomenclature. Longest chain is different, hence that is the idea. Then you have position isomerism. Now in position isomerism, what happens is the position of the functional group is different. You notice that the longest chain is the same in both of these cases, but the position of the isomer, the position of the functional group is a little different in both of these isomers. Then you have functional isomerism. What about functional isomerism? You have the same overall formula, yes, C2H5OH, but both of them are totally different in their properties. Those two have different functional groups. The first one is an alcohol, ethanol. The second one is a dimethyl ether. Fine. Now for functional isomerism, there is an important table that I will give you over here. Please make sure you take a screenshot of this. I will give you 5 seconds. 5, 4, 3, 2 and 1. Take a screenshot of this, my dear friends. You can pause the video over here. It just tells you that if this is the condensed formula, then these could be the possible functional groups that you can get out of it. For example, CnH2n plus 2O, the example that we just saw, you can get alcohols and ethers out of this particular condensed formula. This table will be very helpful while solving those integer type questions where they ask you how many isomers exist for a certain given formula. Okay? So please make sure you note this down, revise this, because we will apply this in the question solving class that is there tomorrow. Now at the end of structural isomerism, we understood that these isomers do not exist with each other. They can't be, they can't be in equilibrium with each other. But there is one such very specific and weird isomerism that is called tautomerism. In the case of tautomerism, these two functional isomers are in equilibrium with each other. On the left hand side, we have a ketone, and on the right hand side we have an enol. So this type of a tautomerism is known as keto-enol tautomerism, and we have discussed this in a lot of detail when we studied epic GOC. Yeah, so keto-enol tautomerism, these two are in equilibrium with each other. The mechanism of keto-enol tautomerism, we can discuss that in aldehydes and ketones chapter. We've already discussed that someday, so you can go back and watch the classes or revise your chapters from wherever you want, in case you want to know the mechanism of this. That is just one form of tautomerism. Other forms of tautomerism also exist. These are not important to remember. Okay, it's not important to remember these. याद रखना है रख लो, तुम्हारी मर्जी है. It's totally your call if you want to. I'll just show you these examples. You have nitrosooxime, nitroacai, imine, enamine, and amidoimidol. In all of these cases, there is one thing that is common. There is a -M group and there is an alpha hydrogen. If you have an alpha hydrogen to a -M group, let's try to understand this over here. -M group, and this is the alpha hydrogen. If there is a -M group and alpha hydrogen, this alpha hydrogen can migrate to the corner of the -M group, and that is what tautomerism is. Everywhere the same thing is happening. -M group, alpha hydrogen. -M group, alpha hydrogen. -M, alpha hydrogen. -M, alpha hydrogen. That is the crux. That is the basic idea behind when tautomerism will exist. Fine. Awesome. Now people going towards the last leg of organic chemistry, GOC, and that is stereoisomerism. The most entertaining bit of GOC is stereoisomerism. Once again reminding you that this is a revision class, so we are not going into all the nitty-gritties. If we did that, this revision class would be of 5 hours. And we definitely don't want to do that. This is a class, not the lockdown. So first of all, geometrical isomers. You could have restricted rotation. That restricted rotation can happen because of double bonds. That restricted rotation can happen because of an entire ring. Okay, and because of that, when you have different orientations of the substituents on both the sides of the ring, you get different isomers. So if you have the substituents on the same side, cis. If you have substituents on the different side, trans. Everyone knows cis and trans. Yeah, this guy is cis, this guy is trans. Very simple. Geometrical isomers are because of restricted rotation. Then you have optical isomers, and the fun thing is that at the time I'm releasing this live session, this video, a whole series on optical isomerism is going on the channel. In case you want to watch that, please make sure you go and visit the playlist of our channel. Optical isomerism, what happens is that there are these certain molecules which are asymmetric in nature. Asymmetric means that their mirror image does not superimpose. Yeah, this is the first guy, this is the second guy. Mirror image does not superimpose with the first guy. This implies that these particular substances are chiral in nature. Chirality means that whenever you shine light on them, they will rotate that light in different directions. They will rotate plane polarized light in opposite directions, and that is when we call these two compounds optical isomers of each other. And a fancier name for these two is enantiomers. Fine. In enantiomers, we also learn about RS configuration. We'll come to that very soon after we revise CIP rules. But this is the idea of optical isomerism. Mirror images not able to superimpose on each other. Then you have conformers. Conformers exist because of free rotation across the sigma bond. So if this is the sigma bond, my pen, this is one of the groups, this is the other group. Because of free rotation, you can have multiple orientations. Yeah, my thumb is overlapping with the thumb. My thumb is at an angle with the thumb. My thumb is totally opposite of my thumb. These different orientations in which these structures can exist are known as conformations. Theoretically speaking, there could be infinite conformations for any specific atom, but there are certain conformations that we discuss, which we will see on the next page. So as you can see, this is one certain conformation. If we rotate it by 60 degrees, we get a different conformation. Fine. Great. So my dear friends, before we get into more details about conformers in this revision, you have to quickly tell me, is this an E isomer or is this a Z isomer? EZ, Entgegen-Zusammen nomenclature. Quickly, let's revise that. So we have to assign priorities to these 4 groups based on CIP rules. Yes, CIP rules says that you have to look at the atomic number first of all. Higher atomic number equals to higher priority. If the atomic number is same, then you have to give higher mass the higher priority. Alright, for thorough revision of CIP rules, please join me in tomorrow's class at 8 p.m. But for now, if I have to give the priority, iodine first, bromine second, chlorine is third, and fluorine is the fourth. Fine. My dear friends, if I have to talk about Entgegen-Zusammen isomerism, what we have to see is what is the priority of these groups on these 2 different sides of the double bond. On the left hand side, iodine is first priority, chlorine is second priority. On the right hand side, bromine is first priority, fluorine is the second priority. Do you realize that now the first priority groups, the highest priority groups are on the same side, the low priority groups are on the same side? Yes, my dear friends, this implies that this is the Z isomer. Okay? Same priority towards the same side, Z isomer. How can you remember this? You can remember this by becoming a little Italian and calling it ZM and opposite. So instead of calling them opposite and same like an Englishman, you can call it ZM and opposite like a pseudo-Italian. Very weird way to remember it, but it works. Okay, cool. Moving on. Then in optical isomerism, if I come back to this structure, can we write the RS configuration quickly? For the left hand side isomer that we have over here, first priority, second priority, third priority, fourth priority is already at the back. So this is S configuration, and similarly the enantiomer would be R configuration. You can verify that. Cool. More details again while we are solving questions tomorrow. To determine whether a structure is optically active or not, you can take its mirror image and try to superimpose. That's the most basic idea. Otherwise, what you can do is you can try to find these symmetry elements. If there is a symmetry element inside a structure, that structure will become optically inactive. So the first 3 examples are of planes of symmetry. What happens in a plane of symmetry? You are able to break the compound into 2 equal halves imaginarily. Fine. You can see the planes of symmetry in the first case. In the second example over here, we have centers of symmetry. Yes. Center of symmetry में क्या होता है? Passing through the center, you are able to join these diagonally opposite ends to each other. Yeah. CH3 is diagonally opposite to another CH3. COOH is diagonally opposite to another COOH. Hydrogen is diagonally opposite to another hydrogen, so on and so forth. This gives you center of symmetry, and if you have center of symmetry, the compound will be optically inactive. Now finally coming to the examples of conformers. Conformations of, what are these? ये किसके conformers हैं? This is conformations of butane. Yeah. So my dear friends, when these groups are right in front of each other, like I'm showing you in the camera, yeah. If these groups are right in front of each other, we call this an eclipsed conformation. If these groups are different, okay, if these groups are not overlapping each other, we call it a staggered conformation. So the general name is eclipsed, staggered, and if these two are totally opposite of each other, we'll call this an anti-configuration. Okay, so eclipsed and staggered are the general names. Now depending on different compounds, we can give them specific names. So over here, when CH3 is overlapping with CH3, we call it fully eclipsed. The dihedral angle, you know what dihedral angle is? The angle between 2 of my fingers right now. Dihedral angle 0 degrees, dihedral angle 60 degrees, something like that. So when dihedral angle between the 2 CH3s is 0 in butane, it is fully eclipsed. When the dihedral angle is 60 degrees between these 2 CH3s, we give it a special name and we call it the gauche structure. That is what gauche is. A lot of people wonder what gauche is. Okay, it's not gauche, gauche. Then if you have CH3 overlapping with a hydrogen that is partially eclipsed or partly eclipsed, it is an eclipsed form, but not totally, because CH3 and CH3 are not in front of each other. Then you have the staggered or anti form, completely opposite to each other. And then once again, over here you will get the partly eclipsed, you will get the gauche over here, and you will get the fully eclipsed. This is the energy level diagram of all of these conformations. The most stable is the anti-conformation, the most unstable is the fully eclipsed conformation. Fine. And the energy gap between these two conformations is so small that they just keep on interchanging. You cannot separate one conformer from the other in the case of such simple structures. Fine. Great. Now coming to cyclohexane. Cyclohexane is so beautiful. It has so many different variations in it. Yeah, the most stable variation of cyclohexane is its chair form. Everyone knows the chair form of cyclohexane, and in the chair form, if I have to draw it, it looks something like this. Yeah, I'm pretty sure you can imagine a very beautifully weird looking chemical chair over here. Yeah, and in the chair isomers, there are two types of substituents that can exist. One of these is known as the axial, and the other is known as the equatorial. Okay, axial substituents are pointing away from the, axial substituents are pointing towards the top or the bottom, equatorial are pointing in this horizontal plane itself. Fine. So if I have to mark all the axials and equatorials, these are the axials which I will draw in the red color. These are the axial substituents that can exist. For now, these are just hydrogens, and then these are the equatorials. Fine, cool. Axial and equatorial. So while solving questions, we will understand more about cis or trans between axial and equatorial, etc. But you know that the chair conformation of cyclohexane is the most stable. Then you have an unstable form, half chair. You have the twist boat, twist boat, half chair, and chair. My dear friends, when the chair flips from one chair to the other chair, if this flip happens, then what will happen? The axials will convert into equatorial and the equatorials will convert into axial. Okay, so what it might look like if I try to do the ring flip. Okay, I'll try to do a ring flip over here in case you want me to do that. Okay, if this is the ring flip that has happened, if this is carbon number 1, okay, the axial bond, which was the red colored bond, will now become the equatorial bond. Okay, this is the carbon number 1, and the equatorial bond, which is green colored, will now become an axial bond. So axial switch to equatorial, equatorial bonds switch to axial when a ring flip occurs. Okay, fine, cool, awesome, great. My dear friends, with this, in just 40 minutes, what we've done is we have revised all the basic ideas of general organic chemistry. I agree that general organic chemistry is so vast, if I have to go into details, it will take a lot of time. In case you want to learn all the nitty-gritties, all the details, all the fancy ideas behind general organic chemistry from scratch, then what you can do is you can go and watch this beautiful web series that I've created called Epic GOC. It is just a YouTube search away. You can just search for Epic GOC on YouTube, or you can just enter this in your web browser and you'll be redirected to the playlist of Epic GOC. Some people would be asking in the chat box that, sir, what about nomenclature? See, nomenclature is a very easy topic in the sense that the questions that come for nomenclature in JEE, you can just look at the options and answer the questions. So to revise nomenclature, simply read the NCERT once. NCERT has like 5-6 pages of nomenclature. Just read that and that would be enough. You can revise that from any source online as well. Just give it a read and that will be enough. Fine. Whew. And as I said earlier, GOC is incomplete without practice. So in tomorrow's question solving session, we will actually get into the dirty bits of general organic chemistry, trying to solve the toughest of questions that I can find. Fine. So people, I hope this revision was helpful. If it was helpful, please hit that like button and don't forget to join me for other sessions. Don't forget to subscribe to Catalysis.